Good evening, everyone. We are in the week 9 problem solving session of the NPTEL course, Control and Tuning Methods in Switched Mode Power Converters. And week 9 is about large signal model and nonlinear control. I am Teja Golla, a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. So I hope you can see my screen. So in the previous weeks, we have discussed about the modeling of converters, and then we have also discussed about the circuit averaging techniques, different techniques to obtain the small signal transfer function. And using the small signal transfer function, how can we design the controller for various control techniques like voltage mode control and current mode control. We have also discussed about the architecture of those. Now, before we move to the large signal model, we need to know about the trajectory. So we also need to know how to draw the phase portrait. So in this week, we are going to learn about various things. So we are going to learn about the phase portrait, as well as we are going to learn about the trajectory. So how to get the phase portrait of a given system, how to learn about the stability of the system, eigenvalues, eigenvectors. So we are going to learn about various things. But first, I would like to start with the average model that we do using Taylor series expansion. So averaged nonlinear model. Average nonlinear model using Taylor series expansion. Using Taylor series expansion. So we know that any model can be written as a function of its state. So let us consider one average. So that's why we are taking the mean. So that's why we are writing x bar dot. So which is a function of the average states as well as duty ratio as well as V. So now if we apply the linearization around an equilibrium point, we can write the Taylor series expansion. Similarly, if we have an output y, say it's a function of x and then x bar, d, and v. So we know that we can write the x perturb tilde dot. If we linearize, we can get something like this. So we'll get dou f by dou x bar at its steady state into x tilde plus hello Joshi, can you hear me? Hello Joshi. Hello Joshi, can you hear me? Hello. I can't hear you. You're talking. Can you hear me? Hello. Hello Joshi, can you hear me? Hello, if you can hear me, can you please confirm? Okay. So whatever I was discussing, so I was discussing regarding the average nonlinear model that we obtain using the Taylor series expansion. So I have considered the model as a function of f as well as the output as a function of h. So now we know that dou f by dou x bar into x butter and then dou f by dou d at steady state into d butter plus dou f by dou v at steady state into v in butter plus all higher order terms which we are ignoring. So all these we are ignoring and tending to zero. So now this is my say A matrix, and then say this is my B matrix, and then this is my E matrix. So I will get x tilde dot as AX butter plus V into D butter plus E into V in butter. Okay. So now in the similar way, we can also get for Y butter. So you can get Y butter dot is equal to C into X butter plus say D into D button. And say it is not dependent on input, or even if you want, you can consider it to be like F into V in butter. So, but let us, okay, for to generalize, we can consider F into V in butter. So now we have two equations that we have obtained from the original nonlinear model after linearizing around the equilibrium point of the Taylor series expansion. So now we know that the given dynamics are as a function of f as well as a function of h. So Naveen, can you hear me? Hello, Naveen. Naveen, can you hear me? Hello, Naveen. Hello. Hello, Naveen. Okay. So the f or x part of dot, I can write it is something like this. So I have x average dot is a vector. Say its functions are f1 and f2. We also know x vector, it's an x1, x2. Similarly, D is scalar, V is scalar, H is scalar, rest of the things are scalar. So now, if I want to get the A matrix, I have to differentiate f with respect to x. So I can get my A matrix as dou f by dou x bar. But both of them are scalars. Sorry, both of them are vectors. So how do we differentiate? So now we have to differentiate each of the vector of f with each of the vector of x, and then we have to continue. So the expression will look something like this. So it will be dou f1 by dou x1, dou f1 by dou x2, and then we have dou f2 by dou x1, and then dou f2 by dou x2. So this is called Jacobian matrix. Similarly, if we calculate B, how are you getting B? B is nothing but dou f by dou d, right? So what is my f? F is a vector, d is scalar. So how are we going to get it? Again, we are going to get a vector because we have to differentiate each of f1 with d. So now we are going to get dou f1 by dou d and then dou f2 by dou d. So this is my A matrix as well as B matrix. So now if we have to calculate my C matrix, then I have to differentiate it with V. So again, we are going to get a matrix which is dou f1 by dou V as well as dou f2 by dou V. C matrix. Now, for getting D matrix, we will get dou H by dou X vector. So here H is scalar and X is vector. So we need to differentiate H with different scalars in the X vector. So now we are going to get something like this. We'll get dou H1 by dou X1 and dou H2 by, sorry, dou H1 not H1 because it is just a single scalar. So let me rewrite it. So it will be dou H by dou X1 and then dou H by dou X2. So this is AB, and then I think this is not C, this is E matrix. My bad. So this is my E matrix. And then this is my C matrix. Sorry. So this is my C matrix. So the C is dou H by dou X. And then now we have to get D matrix. D is with respect to D and F is with respect to F. So now my D matrix is differentiation of a scalar with respect to another scalar. So it simply remains that. So now my F matrix is also differentiation of scalar with respect to scalar. So this is how we are going to get the linearized model from the original nonlinear model. So if we are given a nonlinear model, so then how are we going to get the linear model? So that's what we have discussed till now. So originally we have the dynamics x averaged. Again, we have averaged it and then we have linearized it around Taylor, around an operating point using the Taylor series expansion. So x average dot is a function of x average dynamics as well as duty ratio being similarly y is a scalar. So maybe I'll just mention it here. So here f is a vector and then h is a scalar because the output y is scalar and x is vector. So maybe right here. So this is a vector and then this is a scalar. So now if we have vectors and then scalars, so then how are we going to linearize it and how are we going to find all the matrices? Because sometimes we need to differentiate a vector with a vector, vector with a scalar, and scalar with a vector, and scalar with scalar. So we have all kinds of possibilities that we can obtain. So A is a differentiation of a vector with respect to a vector. B is differentiation of a vector with respect to scalar. C is differentiation of a vector with respect to scalar. E is differentiation of a scalar with respect to vector. D and F are differentiation of two scalar quantities to scalar quantities. So this is how we get a overall model, and then what all we could get from the nonlinear model. So after linearizing this model, Then say we need to find the equilibrium point, if we need to find the eigenvector, if we need to find the eigenvalue, and if we need to find the stability of the equilibrium point, then how are we going to do? So now we are going to discuss about how to get all these details regarding eigenvalues, eigenvectors, as well as trajectory, which is important, which will give information about the phase flow rate, as well as if you want to find the stability of the equilibrium point, how are we going to do that? So till now, any questions? Uh, Naveen, are you able to hear me, Naveen? Hello, Naveen. Hello, Naveen. Can you hear me? No audio and video. Okay, let me reshare. Hello, am I audible now, Naveen? Yes. Okay. Is my video visible? Yes. Okay. So let me quickly summarize what we have discussed. So before getting into the dynamics of the system, what I have started with is I was just discussing about the average nonlinear model, how we are going to linearize it around a Taylor series expansion. So this is all what we have studied earlier, but I have just quickly summarized. So now we are given with function for the state vector as well as the output, which is a scalar. So now if we linearize it around an equilibrium point, then we can get the small signal model, something like this. And higher order terms we are ignoring, so I'm considering it to be zero. So now how are we going to get the A, B, E matrix as well as C, D, and F matrices? So A matrix can be obtained by differentiating F with respect to X. But both F and X are vectors, so we'll get a 2 cross 2 matrix where we are going to differentiate f with all the x as well as differentiate uh, individually. So in the first row we have f1 differentiated with x1 and x2. In the second row we have f2 differentiated with x1 and x2. So this is called Jacobian matrix. Similarly, B, it's a vector differentiated with scalar. So we'll get dou f1 by dou d, dou f2 by dou d. Similarly, if we go to E, then we'll get dou f by dou v. F is vector, so we'll get a column matrix. If we go to C, it's dou h by dou x. H is scalar, x is vector, so we'll get a row matrix. D and F are scalars differentiated with scalars, so we'll get single quantities. So is this clear until this point? Then we'll move to the next topic. Okay, so now let us discuss about the dynamics of the first order LTI system. So I'm starting with the dynamics of LTI system. So now we are going to discuss about the first order. Hello Naveen, can you hear me now? And are you able to see my screen? Because I have just checked with my friend. He says he can see my screen. Hello Naveen, can you hear me? Okay. So say we have the first order system and the expression can be written as something like this. Dx by dt is equal to a into x. And say initial condition x of 0 is x naught. So now how are we going to solve for this? So we can bring x this side dx by x is equal to integral a into dt. So now I can put the limits from say 0 to t. So x of 0 is x naught. So to x. So now if I integrate, I will get ln x varying from x naught to x, varying from x naught to x, which is equal to at. Right. So now I can get ln of x by x naught to the base e is equal to at. So from this we can get x is nothing but x naught into e to the power 8. So this is the final expression that we have gotten. Right. So let us assume that initial condition x naught is positive and say a is negative. Say I'm considering case one. X naught is positive and then a is negative. So in that case, if we draw the x of t, say it is started. So it starts at x naught and then it exponentially decays. So with time it will exponentially decay where this is time. So now let us consider another case, case 2, where we have x naught say positive and say a is also positive. So it will exponentially increase rather than decreasing like case 1. Now it is going to increase. So we have time t here and x of t here. So now it is going to x naught. Okay. So now it is exponentially increasing because a is positive, so the value will keep on increasing. Whereas in the first case where a is negative, it will keep on decreasing. So the x of t will decay with time and then tends to 0, and x of t here will keep on increasing and it will tend to infinity. So just to quickly summarize what we have discussed in the first order dynamics of LTI system, we have considered by first order system whose differential equation we have considered, and then we have integ integrated to find the solution of x, which is x naught into e to the power 80. So now we have considered two cases where x naught is positive in both of them and a is positive in one and a is negative in the other case, and then we have seen that in one case it is increasing and in the other case it is decreasing. So is this clear until this point, Naveen? Hello, Naveen. Yes, sir. Okay. So now let us quickly solve a few problems. So consider a first order LTI system with the following dynamics. So now I would like to ask you. So now I'm asking, draw the x of t as a function of time t. So in this case, what we are going to do is we are going to draw x of t. So first we'll have to solve for x of t and draw its value or draw its and draw as a function of t. So first we have to solve for x of t and then we have to draw it as a function of t. So can you tell me for first question, what will be the x of t? Naveen? Can you tell me what will be x of t in the first case? Okay, maybe I'll give you a hint. So if you see uh, this expression, so we have solved for x of t. So this is like a generic solution, or maybe I'll write. So if you have dx by dt equal to ax, and initial condition x of 0 is x naught, then we have gotten the solution as x of t is equal to x naught into e to the power 80. So now for this case, what will be the solution? Now can you tell me for first case? Okay. So in the first case, the solution will be x of t is equal to x of 0 into e to the power 80. So e to the power 5t. So this is our solution. Now if we draw its waveform, we'll be getting something like this. So it starts with 1 and then it will exponentially increase. Exponentially increase, yeah. Very good. So this is the value 1 and then it will eventually exponentially increase. So in the second case, we have minus 2x and 10. So if we write the expression, x of t is equal to 10 into e to the power minus 2t. So x naught into e to the power minus 2t. Very good. So here x naught I have given 10. So that's why we'll get 10. So now whether this will exponentially increase or decrease. So we have x of t exponentially decrease. Very good. So it will start from 10 and then it will eventually decrease. So this is my 10. Now, third case. So in third case, we have dx1 by dt equal to minus x and x of 0 equal to minus 2. So what will be the x of t in this case? Minus 2 e to the power x, e to the power minus x. So minus 2 into e to the power minus x. So x of t is minus 2 into e to the power minus x. So it will be slightly different. So in this case, what happens is, if this is my y-axis and this is my time period t. So now it will start from minus 2 and then it will eventually decrease. So here it will start from minus 2 because at t equals to 0. So this is, sorry, e to the power minus e to the power minus t. So this is e to the power minus t and this is x of. So it will eventually tend to 0. So now coming back to the fourth point. Okay. So coming to the fourth point, we have dx1 by dt equal to 2.5x and x of 0 is minus 5. So in this case, what will be x of t? Yes, minus 5 into e to the power 2.5x, not minus because it is plus. If it is a, it is a. So that's why, yeah, minus 5 into e to the power 2.5 t because it's a function of t. So x of t is, what did I give? Minus 5, right? Minus 5 into e to the power 2.5 t. So now it will start from minus 5 and then it will exponentially increase in this direction. So this is -5, and then it will exponentially increase because the coefficient is positive. So in this way, we can draw the dynamics of first order by solving for it, and then we can draw its waveform as a function of t. Is this clear? Yes. Okay. So now we'll quickly go into the dynamics of an LTI system, which is a second order. So, and then we'll solve a couple of problems. So first I'll quickly summarize theory. So if you have any doubts, it will be clarified. But if you have any questions, you can also ask. So now we are going to discuss about the dynamics of an LTI system, which is like second order. Okay. So now let us consider a second order system. First of all, decoupled. So when I say decoupled, then x1 and x2 do not have any relation. So what I'm trying to say is say x1 dot equal to -2x1 and x2 dot equal to -3x2. So now this can be written something like this in the matrix form x1 dot x2 dot. We have -2, 0, 0, -3 into x1, x2. So we can write something like this. So if you see, there is no relationship of x1 on x2 as well as x2 on x1. So this is called a decoupled system. So this is called a decoupled system, and this is called matrix A. Okay. So now we have the matrix A. So now, do you know how to find the eigenvalues of this? -2, -3. Very good. So because it's a decoupled system, you can directly look at it and say it is not a decoupled system. Then how to find? So in that case, we have to. So for calculating eigenvalues. So we'll have lambda I minus a equal to 0. So we need to calculate the determinant of this to get the lambda value. So if I do this, I'll get lambda plus 2, 0, 0, lambda plus 3, and then determinant of this is 0. So if you do that, we'll get lambda plus 2 into lambda plus 3 is equals to 0. So from here, we'll get lambda equal to -2 comma -3. So this is how we get lambda value. So these are the eigenvalues. Okay. So now can you tell me how to calculate eigenvectors? Can you help me with calculating the eigenvectors? So AV equal to lambda V, very good. So we'll have two vectors, one for each of the eigenvalue. Say my eigenvectors are Vx and Vy. So both of them are actually vectors. So it has two components. So I'm considering my Vx to be Vx1 and Vx2. Similarly, my Vy to be Vy1 and then Vy2. So now if I do this, and as you said, we'll do A into Vx equal to lambda into Vx. Say, let me assume that this is associated with -2. This is associated with lambda equal to -3. Then I can say that A into V x is equal to lambda into Vx. Say this is lambda 1 and then this is lambda 2. So lambda 1 into Vx. What is AVX? AVX is -2, 0, 0, -3. So we have -2, 0, 0, -3 multiplied by Vx is Vx1, Vx2 equal to, sorry,
equal to minus 2 into Vx1 and Vx2, right?
Agree? Yes. So now if you see,
You will get two equations. One is minus 2Vx1 equal to minus 2Vx1, which is always valid. And then you will get another equation, minus 3Vx2 equal to minus 2Vx2. So now from this we can get that Vx2 is equals to 0.
and Vx1 can be anything. So Vx1 can be 1, Vx1 can be 2, Vx1 can be 3, in like any big number. So we have a
Vx. So from here we can get Vx is say some constant k and then 0.
So now if I have to find the unity vector, then what will I do? I will I will divide it with its value. The value of this vector is k.
So if I have to calculate my unity vector, then I'll get Vx is 1, 0. Agree? So now this has a unit length.
So this has unit length. Similarly, if I do for the other lambda,
Then I can do A into Vx is equals to minus 3 into Vx. So we'll have minus 2, 0, 0 and minus 3. If we multiply Vx1 and then Vx2, and then we'll have minus 3 into Vx1 and Vx2. So we have minus 2 Vx1 equal to minus 3 Vx1, and then minus 3 Vx2 is equals to minus 3 Vx2. So from the first equation, we can get the Vx1 is equals to 0. So now,
sorry, this should be Vy, my bad.
so this is another vector. So we have to use Vy. So A into Vy equal to minus 3 into Vy. So this also has to be something same. So this will be Vy1, Vy2, Vy1, Vy2. Similarly, all this should be changed accordingly because that's the notation we have considered. So minus 2 Vy1 equal to minus 3 Vy1, and then minus 3 Vy2 is equals to minus 3 Vy2. So now from here you will get Vy1 equal to 0 and Vy2 can be anything. So now if I write Vy, it will be 0 and 1. So this is the another unit vector which is also having unit length.
Clear? How we are getting the vectors as well as how we are getting the eigenvalues for a second order system. Naveen, is this clear? Vx equals to 0 by. So if you see my first equation, it is minus 2Vy equal to minus 3Vy1. So if you bring 3y1 this side, you will get Vy1 equals to 0. And then the second equation is always correct. Minus 3Vy2 equal to minus 3Vy2. So I can take Vy2 any length, right? So my Vy1 is 0. I can take Vy2, say some constant k. So now if I have to connect it into convert it into unit length, then I'll convert into unit length by dividing by its magnitude. So here I have k0. K0 has become 1, 0. Here I'll have 0 into k. So 0 and k, if I divide by k, then it will become 0 and 1, which is unit length. So is that clear? Yes. Okay. So now can you tell me about the stability of the system based on the eigenvalues? Whether it is stable, whether it is unstable, or uh, any intuition from based on the stable? Yes. So because they are negative, it is stable. So it is stable. So before we start solving couple of problems, I would like to comment on the stability of the second order LTI system.
Stability of the second order LTI system. So we have multiple cases. Let me explain each and every case. If you have any doubts, please stop me. So first we are going to consider case 1, which is lambda 1 less than 0 and then lambda 2 less than 0. So this is called stable node because both are negative. And say this is my x1, x2. So in such case, the trajectory will be something like this. So it will go towards the origin. So you will take the point anywhere, it will go towards the origin. So this will be the trajectory of the stable node. So if you take on the axis, then it will, we cannot say if whether it will go along the axis or not, depending upon the eigenvector. So like uh, anywhere you take, it will go towards the origin. So that's why it is called stable. So is this clear, Naveen? Yes. So now let us consider another case where we have lambda 1 greater than 0 and then lambda 2 also greater than 0. So this is called unstable node because both are positive. So now if we draw the similar kind of diagram and then see the trajectory. Say this is x1, x2. Now it will move away from the origin. So if we take a point here, it will go away from the origin. Here also, it will try to go away from the origin. Away from the origin. So you take any point other than the equilibrium point, it will try to go away from the origin. This also clear, Naveen? On axis. So if you take on axis, then also it will go away from the axis, but depending upon the eigenvector. Say eigenvectors are along the axis, then in that case, it will go like this, it will go like this, it will go like this, again it will go like this. So if the eigenvectors are on the axis, then it will go along the eigenvector outside from or away from the origin. Say if the eigenvectors are not along this or like along the x and y axis, then it will not be straight line, but it will be still moving away from the origin, but it will have a different way. Like maybe I'll tell you. Say my eigenvectors are say something like this, and then something like this. So now, if you take any point here, it will go towards the along the eigenvector. Eventually it will go along the eigenvector, and then it will move away. But because here we have considered the eigenvectors along the axis, it will move. So in this case, if you consider any point on the eigenvector, it will go along the eigenvector. Here also, if you consider any, it will go along the eigenvector. So any point on the eigenvector will travel on the eigenvector, but anything outside the eigenvector will try to come towards the eigenvector as time passes. So is this clear? Yes. Now let us consider another case. So third case, say we have one stable and one unstable. So say lambda 1 is positive and then lambda 2 is negative. Can you tell me what is this equilibrium point now if one is stable and another is unstable? Do you know what this is? Unstable. Okay, not exactly. One of them is unstable, another one is stable. So this is called saddle point. One of them is stable, another one is unstable. So this is called saddle point. Okay. So now let us draw. So now if you see which is stable, lambda 2 is stable. Lambda 1 means x1 is unstable x2 is stable. So this is x1, this is x2. So x2 is stable. So if we take anything here, x2 will try to take it to the origin and x1 will try to take it away from the origin. So it will go something like this. If we take from here, it will go something like this. If we take anything here, it will go something like this. So x2 will try to take it to the origin, x1 will try to take it away from the origin. So that's why the direction will be something like this. So it will move to infinity uh, around the x1 axis, but x2 it will try to take it to the origin, but from there x1 will try to take it to the infinity because one is stable, other one is unstable. So this is called saddle point. Is this clear? Yes. Okay. Now all these are real cases, right? So now we have discussed about the stability of the second order system when lambda is real. Okay. Now what we are going to discuss when lambda is not real. So now what we are going to discuss is lambda is complex. So lambda is complex. So now like how we have three cases, here also we'll have three cases. Let us discuss one by one. So here just to say we can consider lambda is equal to r plus or minus j omega. So it has to be conjugate because the system is real. So the A matrix is real. So we'll have two eigenvalues or four depending upon the order of the system. It cannot have odd number of complex numbers. Then the system should be complex because A matrix, if it is real, then the eigenvalues will come as a pair, conjugate pair. So it will be r plus or minus j omega. So now the first case, r is positive. So can you tell me whether it is stable or unstable? Unstable, very good. So if R is greater than 0, then it is unstable and then it is called unstable focus. So say if we take any point here, so it will move in a spiral way, but it will move away from the origin. So it will go something like this. So in this case, I have considered clockwise orientation, but it can be anti-clockwise as well. So it can go something like this also. It can start from here and then it can go in this way also. So how are we going to know whether it is clockwise or anti-clockwise? For that, I have considered one problem. So in that problem, we are going to know where I'll tell how to solve. By considering one numerical, I will explain. But if it has unstable focus, it will move away from the origin in a spiral way. Is this clear, Naveen? Yes. So now the next one we are going to take is a stable case. So case 2, r is less than 0. So we have stable focus. So in the case of stable focus, as it is stable, it will spirally come towards the origin. So if I take a point here, say if it is coming clockwise, then it will come and then it will meet here. So this is going clockwise, or maybe clockwise I use different colors. So I can make it red. Also I can make it red. Okay. Similarly, if it is anti-clockwise, then how will it look like? So if it is anti-clockwise, then it can come something like this. So it is going anti-clockwise. So it is stable because it is coming towards the origin. So now we have considered two cases. Now let us consider the third case where r equals to 0. It means it is what? Purely imaginary. So plus or minus j omega. So in this case, it is called center. And then how it will look like? So it will be just a circle. So it will neither go inside nor go outside, but it will go in a circle, say clockwise direction, or it can be anti-clockwise as well. So clockwise here and then anti-clockwise here. So wherever it starts, say this is our initial point. Wherever you take, it will go in a circular man for circular fashion, but here it is in anti-clockwise. So who decides the uh, clockwise or anti-clockwise direction that we are going to solve a problem, and we'll know. But is this clear how we are deciding the stability of the second order LTA system? Yes. Okay. I'll just quickly summarize what we have discussed before we solve problems. So it will be like quickly summarized. So we have considered second order dynamics. Previously, we have considered first order dynamics and quickly solved one problem. So in the case of second order, we have considered first a decoupled system, which means the dynamics of x1 are independent of x2. Similarly, dynamics of x2 are independent on x1. And then we have obtained the A matrix. Then we have seen how to find the eigenvalues. We can find by calculating the determinant of lambda I minus A, and then by calculating the lambda values, we can get the eigenvalues. So from the eigenvalues, we can tell whether the system is stable or not. And then we have also discussed in detail in the upcoming slide. How to find eigenvector? We have to calculate AV equal to lambda V. So for each eigenvector, we'll have one eigenvalue, or for each eigenvalue, we'll have one eigenvector. So if it's the second order system, we'll have two eigenvalues, which means we'll have two eigenvectors, and we have solved. And then we have seen they are along the x-axis as well as y-axis. So if you see, this is along the x-axis and this is along the y-axis. So we have two eigenvectors, two eigenvalues. After this, we have asked our question, question to ourselves, how to determine the stability of the system, where we have realized that first of all, lambda can be real or lambda can be complex. So if lambda is real, then there are multiple cases, out of which we have discussed three, which is covered in this course. There are actually many complicated cases as well, but that are beyond the syllabus of this course, so that's why they are not discussed. So we have considered both eigenvalues to be negative, which means it is stable now. So if the initial condition is somewhere, then the trajectory will go towards the origin because it is stable. If we consider both of them to be positive, then it is unstable node. And then if we consider any initial condition, then it will move outside or away from the origin. If we consider on the eigenvector, then it will move on along the eigenvector. If not, then it will move towards the eigenvector and it eventually meet eigenvector at time tending to infinity. So if one of them is positive and other one is negative, then it is called saddle point. So the stable x1 or x2, whichever is stable, will try to take it to the origin, and the other one will try to take it to the infinity. So that's why it is coming something like this. In the next case, we have considered complex eigenvalues, which is of the form r plus or minus j omega. And if r is positive, then it is called unstable focus. It will spirally go away from the origin. It can go either clockwise direction or anti-clockwise direction. If it is stable focus, then it will go towards the origin, whether it is in clockwise or anti-clockwise direction. If r equals to 0 and the eigenvalues are purely imaginary, then it is called center. Then it will move in a circular fashion, not spirally moving out or inside, and it can also be clockwise or anti-clockwise. There is less than a minute. If this meeting ends, kindly join back, then we'll solve a couple of problems. So if you have any queries until this point, you can ask, else let the meeting end. Then once we join, we'll solve problems. Any questions until this point, Naveen? No, sir. Okay, if this meeting ends, kindly join back. Then we'll solve few problems. So solve these problems along with me. So I have considered one second order LTI system, where I have considered one coupled system as well as decoupled system. So this is first one is coupled or decoupled? First one is decoupled, very good. Second one is coupled. So I have given two cases. First one is decoupled and second one is coupled. So now I'm asking what are the eigenvalues and eigenvectors of both of them, and then also find the transformation matrix M, and then find the stability of the equilibrium points and draw the trajectory if the initial condition is this. So first we'll take x dot equal to ax and then do all ABCD, and then we'll take x dot equal to bx and then do all ABCD. So part B is only applicable for this x dot equal to bx. I'll tell you why. Then once we do that, then we'll come back and then solve the rest of the problems. So can you tell me for x dot equal to ax, what are the eigenvalues and eigenvectors? So first we are considering x dot equal to ax. So what are the eigenvalues as well as what are the eigenvectors? Decoupled -2, -3. Very good. So we have already solved. So we can directly tell that my eigenvalues are, say, lambda 1 equal to -2 and then lambda 2 is equals to -3. So from this, we can get that my eigenvalues are -2 and -3. So can you tell me what are the eigenvectors? We have also solved just now, but you can also calculate and let me know. So for anyone who might not have attended, we can calculate that of lambda I minus a equals to 0. And from there, we can get -2 and -3 are the eigenvectors. So are you able to calculate eigenvectors or are you facing any difficulty? Okay. So if you see, previously we have solved for the same condition -2, 0, 0, -3. We have gotten the eigenvectors as 1, 0 as well as 0. So because I have already solved, I am not solving again here. So people who are just watching this video, kindly refer back where I have explained how to calculate the eigenvectors for this particular problem. But for other problems, we are going to solve. So we can get my eigenvectors V1 as 1, 0 and V2 as 0, 1. Okay. So is this clear? We have gotten the eigenvectors, eigenvalues and eigenvectors. Yes. So the transformation matrix M is only applicable for the second part. So we are going to skip it for now. Now, can you tell me regarding the stability of the system, whether it is stable, unstable? It is stable. Very good. So for the B part, we know that lambda 1 and lambda 2 both are less than 0. So that's why it is called stable node. So this is not B part. This is actually C part. So D part. So now D part, I'm asking what is the trajectory if the initial condition is 1, 1, -1, -1. So let me draw the axis first. So this is x1, this is x2. So I am starting one from 1, 1, another one is -1, 1. So how is it going to go?
is it going, will it be going towards the origin or away from the origin? It is going towards the origin. So I can say because x2 is -3, so it is going to pull this more than this. So it will come like this. Similarly, here also it is going to come like this. Because x2 has more force than x1 because it is -3. So that's why it is going to come like this. So it will go towards the origin. Similarly, if we consider an additional case, then also we'll get something like this. Here also something like this. So is this clear, the first part? Okay. So if the first part is clear, then we are going to solve for the second part, which is x dot equal to bx. So x dot equal to x is quite simple and straightforward. We have done. Now we are going to solve the next part. So for that, let us add. So x dot equal to bx. So this is now second part. So x dot equal to bx and b is nothing but -1, -1, 2, -4. -1, -1, 2, -4. So now we are going to solve the first part where we are going to calculate the eigenvalues first. So can you calculate the eigenvalues and let me know? Then I'll solve and then we can cross it. Then we'll also solve eigenvectors. Let me know once you have solved, then I'll start solving. Are you able to solve? Navik? -2, -3. Yeah, very good. So let me quickly solve. So we know that we have to do lambda I minus b. Determinant of this is equals to 0. So I'll get lambda plus 1, then 1, -2, and then lambda plus 4. And the determinant of this should be 0. So now I'll have to calculate lambda square plus 5 lambda plus 4 plus 2 equal to 0. So now I'll get lambda square plus 5 lambda plus 6 is equals to 0. Then I'll get lambda plus 2 into lambda plus 3 is equals to 0. So I'll get lambda 1 equal to -2 and lambda 2 equal to -3. So very good. It is matching. So now we are going to calculate the eigenvectors. So what do you think whether the eigenvectors of this problem and this problem is same? since the eigenvalues are same for both the matrices, whether the eigenvectors be same or whether the vectors will be different. Can you calculate and let me know whether you are getting same eigenvectors as the previous case or different? So 1 for lambda equal to -2, very good. And for the other case, 1, 2, very good. So you have done it so quickly, also correctly. So yeah, let me quickly solve and cross check. So for lambda 1 equal to -2. So first, let us solve for lambda 1 equal to -2 and then for lambda 2 equal to -3. So B matrix is -1, -1, 2, -4. -1, -1, 2, -4. So B matrix into its vector say V1. So then we'll have say Vx1, Vx1 and Vx2 is equal to -2 into Vx1, Vx2. Okay. So once we solve this, we'll get minus Vx1 minus Vx2 equal to -2 Vx1. So from this we'll get Vx1 equal to Vx2. So I can say that my Vx is nothing but 1 and 1 because both are same. So this gives my first eigenvector for lambda 1 equal to -2, which I have calculated correctly. Then we have -1, -1, 2, -4. And then again we have now V by 1. So V by 1, V by 2, lambda is -3 into V by 1, V by 2. So from the first equation, I'll get minus V by 1 minus V by 2 equal to -3 V by 1. So from this, I'll get 2 V by 1 equal to V by 2. So V by 2 is 2 times V by 1. So if I take V by 1 as 1, I'll get 2 over here. So this is my other eigenvector. So yeah, calculated it correctly, eigenvalues as well as eigenvectors. So now can you tell me what is the transformation matrix M? How to calculate? Okay. So if you are not aware, let me just quickly explain about the transformation matrix. So this is about transformation matrix. So say I have x dot equal to ax. So now I have considered one transformation z equal to mx. So what will be z dot? Z dot will be m into x dot. And what is x dot? X dot is m into a into x. So now if I replace x, what is x? X is nothing but m inverse into z.
So now if we finally substitute, we'll get Z equal to M into A into M inverse into Z. Now if I assume this to be some matrix B,
then A and B will have same eigenvalues.
so A and B will have same eigenvalues. Now if you see in the question that I have given,
Both A and B have same eigenvalues, which are -2 and -3. So who decides this M? M is nothing but
the Vx as well as Vy vectors. So my M is nothing but 1, 1 and then 1, 2. So if you are not sure, during your leisure time, you can calculate and see whether my V is M into A into M inverse or not. So once you calculate this, you will have more confidence. So during your leisure time, you can calculate this.
M is there, A is also there. So if you multiply
M into A and then multiply by M inverse, then you will get our matrix B.
So if my eigenvectors is not say 1, 1, 1, 2, say it is 1, 1 and 1, 0, then my B matrix will accordingly change. So for this B matrix, if we calculate the eigenvectors and then if we combine the eigenvectors and get the matrix, that is our transformation matrix M, using which I can transform A matrix into another matrix B, where both of them have the same eigenvalues, but the eigenvectors will be different. So is this clear? So this is how we get transformation matrix M. Okay. So now let us go to the C part. C part is find the stability of the equilibrium points. So tell me for this B case, whether it is stable node, stable focus, unstable node, unstable focus, saddle point. What is it? Stable. Yes. So this is stable.
So it is stable node because lambda 1 and lambda 2 both are negative. Lambda 1 is less than 0. Lambda 2 is also less than 0. So it is called stable focus. Sorry, stable node because it is real. Now in the D part, I have asked what are the trajectory. So first let us draw the plane. This is x1, this is x2.
So let us also draw the eigenvectors. So one eigenvector is passing through 1, 1.
So if I use dash line for the eigenvector and maybe pink color or say orange color. So it is passing through 1, 1, right? So this is corresponding to which one? Lambda 1. This is corresponding to lambda 1, which is -2.
Now, if we are passing through point 1, 2, so 1, 2,
so then it will have a little bit higher slope. Yeah. So now this is corresponding to lambda 2, which is -3. Okay.
So now we are considering 2 points. One is 1, 1. Another point is -1, -1. So 1, 1
is lying over here. So 1, 1 will be on this somewhere here. And -1, 1 will be somewhere here. So now, or maybe I'll use black color. Then we can see black color. Yeah.
So how will the trajectory go? To the origin. Yes, but whether it will go on the line or whether there will be curvature. Correct. Uh, Not exactly. So as I have said previously, in this case, if the initial condition is along the eigenvector, then it will move along the eigenvector. If you see, my points are 1, 1 and -1, 1, -1. which are on this eigenvector. So it will move along the direction of the eigenvector. So it will go straight. So this will be like this, and this will be like this. So now it is going on the line because it is on the line. Similarly, if you consider here this point, it will go on the line here, it will go on the line here. But in the previous case that we have considered, the eigenvectors are 1, 0 and 0, 1. So any point that is lying on the axis, it will move along the axis like this. But other points will go in the curve fashion. Similarly, here, any points that are on the eigenvector will go along the eigenvector towards the origin because it is stable. But anything that is outside will go on the curve fashion. Say, uh, we have a point here. So lambda 2 equal to -3 is having more pull. So it will go something like this. And if you consider point again here, so it can go something like this. Because this has more pull, lambda 2. So other points will go in a curve fashion, but these points will go along the eigenvector because they are on the eigenvector. So is this question clear? Navid, any questions, any doubts until this point? Is it clear or do you have any doubts? Okay. So I assume things are clear. Then we'll solve another problem. Let me read out the problem for you. Consider a second order LTI system with the following dynamics. F1 of x and F2 of x are given. Find all the equilibrium points. Then find the state matrices for the equilibrium points. Find the eigenvalues as well as eigenvectors and comment on the stability of the equilibrium points. So, do you know how to find the equilibrium points? David? Hello, Navin, are you there? Okay. So, to find the equilibrium points, we have to equate the x dot to be equal to 0. So, x dot equals to 0, which means my f1 of x will be 0. Similarly, f2 of x also will be 0. So, if we solve this, we'll get minus x2 equals to 0, which means x2 is 0. Because x2 is 0, now this equation will become 2x1 plus x1 square is equals to 0. That implies x1 into x1 plus 2 equal to 0. So now I'll have two equilibrium points. So one equilibrium point is from here I'll get x1 equals to 0 comma minus 2. So I'll have two equilibrium points. One is 0 comma 0. The other one is minus 2 comma 0. So these are the both two equilibrium points. So these are the equilibrium points. So is this clear how we got the equilibrium points? Navin? By equating them to 0. Okay. So now how to find the state matrices. So previously I have mentioned that if we have any nonlinear system, we have discussed at the beginning, then how to find the A matrix. We have to do dou f1 by dou x1, dou f1 by dou x2, then dou f2 by dou x1 as well as dou f2 by dou x2. So now we have to solve it and then check whether we are able to get that or not.
So now I'm first what I will do is first I'll get the generic state matrix. So I'll do something like this.
So Naveen, are you able to hear me now? Naveen, are you able to hear me? So the generic state matrix
A can be written as A is dou f1 by dou x1, dou f1 by dou x2, dou f1 f2 by dou x1, and then dou f2 by dou x2. So dou f1 by dou x1 is 0 because it is only dependent on x2, and if we differentiate with respect to x2, we'll get -1. So if we differentiate f2 with respect to x1, we'll get 2 plus 2x1. So 2 plus 2x1. And then if we differentiate with respect to x2, then we'll get 2. Okay. So now because we have two equilibrium points, so if we consider 0, 0, then corresponding to that, we will get A matrix as 0, -1, 2, and 2. If we consider -2, 0 equilibrium point, then you will get A, say this is A1. Now we'll get A2, which is equals to 0, -1, -2, and then 2. So is this clear? Naveen, have we got two matrices for two equilibrium points? So in the second part, I have asked what are the state matrices for the equilibrium points. Now we have to find the eigenvalues as well as eigenvalues. So first, let us consider A1. So in C part, let us consider A1 and then calculate the eigenvalues as well as eigenvalues. So I'm considering A1 to be 0, -1, 2 as well as 2. So now if we simplify this, we'll get determinant of lambda I minus A1 is equals to 0. So now if we do that, then whatever we'll be getting, that is lambda I minus A1. So now what are we going to get? Naveen, are you able to hear me? Yes, okay. So now lambda I minus A1. If we calculate, we will get lambda plus 1 minus 2 lambda plus 2. Determinant of this is 0. So if you solve it, you will get lambda square plus 2 lambda plus 2 equals to 0. So can you calculate the eigenvalues for this and let me know what eigenvalues you are getting? The meantime, I can also calculate. Let me know what eigenvalues you are getting. 1, 2, 3. By 1, 2, 3, there are only two, right? 1, 2, 2. No, but by three values, it's a second order system, right? It will have only two unknowns. So if you solve for it, we can get like lambda plus 1 whole square equal to -1. So lambda plus 1 whole square equal to I square. So lambda is nothing but 1 plus or minus j or I. 1 plus or minus I. So that implies lambda 1 equal to 1 plus I lambda 2 equal to 1 minus I. Is this clear?
How we are getting 1 plus I as well as 1 minus I. Okay. So now we are going to calculate the eigenvectors for each of them. So first we'll calculate for 1 plus I, 1 minus I. So basically we had two matrices. For each of the equilibrium point, we got one matrix. So two matrices, two matrices. For each of the matrix now, we are calculating the eigenvectors. So for each matrix, again, we have two eigenvalues. For each of the eigenvalue, we'll calculate the eigenvector. So first I'm considering 1 plus I.
So I'll consider lambda 1 to be 1 plus I, and then I'll solve for the vector lambda to be 1 minus I, and then I'll solve for that.
So for 1 plus I, we need to consider AV equal to lambda V. So AV is 0 minus 1, 2, 2.
So we have 0 minus 1, 2, 2 into Vx1, Vx2 is equal to 1 plus I into Vx1, Vx2. So from this I will get minus Vx2 equal to 1 plus I into Vx1, or I can say Vx2 is equals to minus of 1 plus I into Vx1. So from this I can get my Vx as Vx is nothing but, if I consider Vx1 to be 1, this will be minus of 1 plus I. Similarly, if we do for 1 minus I, then I'll have 0, minus 1, 2, and 2, and then Vy1 and then Vy2 is equal to 1 minus I into Vy1 as well as Vy2. So now if we again equate, I'll get minus Vy2 equal to 1 minus I into Vy1, or I can say Vy2 is nothing but I minus 1 into Vy1. So if we consider my Vy as a vector, Vy1 if you take 1, this will be I minus 1. So this is my another vector for this eigenvalue.
So is this clear how we got the eigen values as well as eigenvectors for the first matrix A? So now we are going to repeat the same for the second matrix, which is A. So until this point, is this clear, Navid? Yes. Okay. So now what we are going to do is we are going to consider the second matrix, which is 0, minus 1, and minus 2, 2. A2.
0, minus 1 and minus 2, 2.
0, minus 1, and minus 2. So can you calculate the eigenvalues and then let me know what you are getting?
In the meantime, I'll also start solving. So we have to do lambda I minus A2 equals to 0. Lambda plus 1. I got lambda 1 to be 1 plus root 3 and lambda 2 to be 1 minus root.
Are you able to get the same eigenvalues?
So let me wait until you solve, then we can cross check.
Are you getting the same eigenvalues? Yes. Okay, now let us calculate the eigenvectors. So for lambda 1 equal to 1 plus root 3, first let us calculate.
So lambda 1 is 1 plus root 3.
So AV equal to lambda V. So 0 minus 1 minus 2, 2.
0 minus 1 minus 2, 2 into Vx1, Vx2 equal to 1 plus root 3 into Vx1, Vx2. So if you calculate the first one, we will get minus Vx2 equal to 1 plus root 3 into Vx1.
So from this, I'll get
Vx2 is nothing but minus of 1 plus root 3 into Vx1. So now I can say that my Vx, if I consider Vx1 to be 1, this is minus of 1 plus root 3. So this is my first eigenvector for the eigenvalue 1 plus root 3.
now my other value is 1 minus root 3.
So we have lambda 2 is equals to 1 minus root 3. So we have 0 minus 1, 2 minus 2 into v by 1, v by 2 is equals to 1 minus root 3 v by 1, v by 2. So from here you can get minus v by 1 is equals to 1 minus root 3 into, sorry, minus v by 2 is v by 1. Or I can say v by 2 is root 3 minus 1 into v by 1. So we'll have v by, if we consider this as 1, we'll have root 3 minus 1. So this is the other eigenvector that we have obtained.
So is this clear till this point how we have calculated eigenvalues and eigenvectors for both the matrices that we have obtained from two equilibrium points of the given nonlinear system? After that, we have linearized. Yes. So now, if we see, first we have calculated the equilibrium points. How did we calculate? Because equilibrium point means x dot will be 0. We have equated both of them to 0, and then we have gotten two equilibrium points. So for now, each equilibrium point, there will be one state matrix. So for any given nonlinear system, we have discussed at the very beginning of the lecture that this is the A matrix. So now using that A matrix, we have obtained the generic A matrix. Now it is dependent on x1 as there are two equilibrium points. We have two A1 matrices. So for each of the A matrix, we have calculated what are the eigenvalues and then what are the eigenvectors. And then we have also calculated for the second matrix. So now the third question is what are the eigenvalues and what are the eigenvectors which we have solved. Now comment on the stability of the equilibrium points. So can you tell me whether it is stable or unstable? First of all, there is less than a minute, so if this meeting ends, kindly join back. So is this stable or unstable? If this meeting ends, kindly join back. We'll solve another problem. So this is unstable focus. Very good. Because it is complex, so that's why it is unstable focus. And then this case, 1 plus root 3, 1 minus root 3. If this meeting ends, kindly join back. We'll solve one more problem before we wind up this session. So this will be saddle point. Because one is positive, one is negative, and both are real. So this is called saddle point. Is that clear, Naveen? So let me just write. So we have A1. Unstable focus and elegant flow. So this is the thing that we got for the first case. And then for the second case, right, this is my A2. So this is A2. And then we got this saddle point. Then we got two things. So these are the two. So A1 is 0 minus 1, 2, 2. So for this, we got two eigenvalues which are found to be unstable focus, and these are the two eigenvectors that we got. Similarly, for the other matrix, we got two eigenvalues. One is positive, one is negative. So this is saddle point. And then we got two vectors for this as well. So is this clear, Naveen, until this point? Okay. So if we see it is unstable focus, right? But how do we know whether it is going clockwise or anti-clockwise? So for that, I'll tell you as I have promised. So let us draw the system. This is x1, this is x2. So now say it is going outside, out of the origin, right? So, but how do I know whether it is going clockwise or anti-clockwise? So consider one point, very close point in the vicinity of the origin. Say I'm considering it as some delta x comma delta x. So I'm considering one point which is delta x comma delta x. So now find fx and fy, which is, so x dot you have to find. X dot is what? Ax, right? So my x is delta x. So if you calculate 0 minus 1, 2 minus 2 into delta x. So if you calculate it, you will get minus delta x and 4 delta x. So this is the direction of the trajectory. So in the x direction, it is negative. In the y direction, it is 4 times positive. So the net direction is this. So now we know that it is going in the clockwise, anti-clockwise direction, and it is going outside. So that's how we get the direction. So this is in this and this is in this direction. So now because we know the direction, that's why we can say that it is in anti-clockwise direction. So Naveen, is this clear how to get the direction of the trajectory, whether it is clockwise or anti-clockwise? We'll consider some close point to the our equilibrium point, and then we'll calculate x dot. So this x dot will give the direction of the trajectory. So in the x1 it is negative, so it is left side. In the y side it is 4 times positive, so the direction is in this direction. So it is going in the anti-clockwise. Is that clear, Naveen? Okay. Similarly, here it is saddle point. So if we draw the final diagram, so this is x1 and this is x2. We know that for x1, lambda 1 is positive, and then for x2, lambda 2 is negative. So this is stable, that is unstable. So my trajectory will go something like this, as we have discussed earlier. So no confusion. Is this clear, Naveen? Then we'll move to the final problem. Or maybe let me quickly summarize. So in this problem, which is very critical, I have given a nonlinear system. So consider I think I should be saying consider a second order system with the following dynamics. So find the equilibrium points, find the state matrices for all the equilibrium points, find the eigenvalues and eigenvectors, comment on the stability of the equilibrium points. So what we have done is first we have to find the equilibrium points by equating x dot equal to 0. I got two equilibrium points. Then I have linearized it to get the A matrix for each of the equilibrium points. So we got two A matrices. For each of the A matrix, I have calculated the eigenvalues and like commented on the stability, as well as for each eigenvalue, I got eigenvectors. So for the first A matrix, I got two eigenvalues, two eigenvectors. Similarly, for the second eigenvalue, I got two eigenvalues. For the second A matrix, I got two eigenvalues as well as two eigenvectors. So this is the summary. This is for the first equilibrium point, and this is for the second equilibrium point. So this A matrix is for which equilibrium point? 0, 0, and the second one is minus 2, 0. So if I have to say this is for the 0, 0 equilibrium point, and this is for minus 2, 0 equilibrium. Okay. So now let us move to the fourth problem, which is already what we have discussed in between, the transformation matrix.
So now we know that Z equal to mx, which means my x is m inverse into Z. So this is the condition that we have to keep in mind.
So now let us solve.
So Z equal to mx means Z dot equal to mx dot, and x dot is given as ax plus bu. So now I will get max plus mbu. So now my Z dot is x is what? M inverse, right? So m inverse into Z plus mb into u. So now this becomes my a dash and this becomes my b dash. Simple.
And then y is equals to c dash z plus d dash u. So y equal to cx plus du.
So we have y equals to cx plus du. And what is x? X is nothing but m inverse into z. So we have c m inverse into z plus du. So with this we'll get, this is my c dash matrix and this is my d dash matrix. So we have my a dash is nothing but m inverse, and my b matrix is nothing but m into b. My c matrix is nothing but c m inverse, and my D matrix will remain the same, and it is nothing but D.
So this is a question on the transformation matrix. I have given the transformation matrix, but kindly keep a note. So in the exam, they can give z equal to m inverse x. So then this will vary. So this is for mx. So for mx, I have converted everything in terms of z and I have substituted it back. So I have made sure that z dot is a dash z plus b dash u. It is in that expression. So I got a dash b dash. Similarly, y equals to c dash z plus d dash u. Then I got c dash and d dash. So this is our final problem for today's session. Do you have any further queries, Navid? If not, then I'll quickly summarize and end this session. Okay, if you don't have any queries, then I'll quickly summarize. So today's discussion in week 9, we have started with the discussion about average nonlinear model using Taylor series expansion. So first we have discussed about how to linearize a nonlinear model around the equilibrium point using Taylor series expansion, and then we have discussed about how to get these matrices, and we have discussed a matrix is also called as Jacobian matrix and how we can get this by differentiating with respect to the x1 as well as x2, and then we have seen how to get all these matrices. Then we have discussed about the dynamics of an LTI system. We have started with first order, and then we have seen what is the solution, and we have also discussed what is the trajectory or the how the x of t will change with respect to time for different cases. Then we have quickly solved one problem where I have considered 4 cases, and then we have drawn. First, we have solved for x of t, and then we have drawn it as a function of t. Then we have moved to the dynamics of a second order system. We have considered a decoupled system, and then we have discussed how to calculate the eigenvalues. And then we have also discussed how to calculate the eigenvectors for these eigenvalues. Then we have discussed about the stability of the second order LTI system. The eigenvalues are real. Then we have considered 3 cases where both the eigenvalues are negative, which is stable node. When both the eigenvalues are positive, it is called unstable node. When one of them is positive and one of them is negative, it is called saddle point. Then we have considered another case study where eigenvalues are complex. And then we have discussed if the radius is positive, then it is unstable focus. If the radius r is less than 0, then it is stable focus. And then if the radius is 0, then it is called center. In all of these cases, it can either move clockwise or anti-clockwise. And how to get the direction we have discussed in the problems. Then we have solved a couple of problems. In the second problem, we have considered two systems. One is decoupled, one is coupled. In each of them, we have calculated the eigenvalues as well as eigenvectors. And in the second case, we have seen how to calculate the transformation matrix M. And then we have also commented on the stability of the system. And we have also discussed the trajectory if the initial condition is given. So in the first case, we have found out that it is stable rho, and then this is the trajectory. In the second case, we have calculated the eigenvalues as well as eigenvectors, and the transformation matrix can be given as Vx, Vy, and then we have obtained the transformation matrix, and then it is stable rho. We have gotten the eigen vectors, and we have seen how the trajectory flows or how the trajectory moves with respect to time. Now, in the third problem, we have considered a nonlinear system, and then first we have linearized it and then obtained the matrix. But as asked, we have calculated the equilibrium points by equating h dot equals to 0, and we have gotten two equilibrium points, and for each of the equilibrium point, we have obtained a matrix. Once we have obtained the A matrix, we have calculated the eigenvalues as well as eigenvectors for both A1 as well as A2, and then we have commented on the stability. So for the equilibrium point 1, we got unstable focus as the stability, and for the equilibrium point 2, we have obtained saddle point as the stability, and we have also discussed about how to calculate the direction. We will consider a close point near the vicinity of the equilibrium point, and then we'll calculate x dot, from which we can get the direction of the this unstable focus. Similarly, for saddle point, this is the trajectory direction. In the final case, we have considered one similar t transformation, which is z equal to mx, and then by substituting, we got a dash, b dash, c dash as well as d dash. So this is the overall discussion for today. If you have any questions, you can ask, else we'll meet again on Monday with week 10. So do you have any queries, Naveen? Okay. So if you don't have any queries, then I'll end this session here, and again we'll meet on Monday with week 10. I wish you all the best for your week 9. Please go through the lectures if you have any queries, and if you want to practice or if you have any further queries, you can go through this problem solving session. I will be uploading it to my YouTube video, and you can go through. So I wish you all the best and see you on Monday. That I'll end this session here.